First part of this lesson is talking about specific heat, how easily water changes its temperature compared to another liquid, in this case, oil. And water changes its temperature much, much more slowly. And that is due to those hydrogen bonds, right? They absorb a lot of energy to break them down. And so that's why water is relatively good at maintaining its temperature, whether it's resisting being heated up or resisting being cooled down, which is why we get things that are, near oceans. If you're right next to the coast and you have a prevailing winds that bring the air off the ocean over land, like you would see in a lot of places in Southern California, if you're close enough to the coast, you get that marine layer that really moderates the temperature, right? Keeps it from getting too hot or too cold compared to what it otherwise would be. So that's just talking about specific heat there. Thinking about chemical reactions, we have two types of chemical reactions that can happen. Now, in any chemical reaction, and we've already kind of looked at this a little bit when we talked about enzymes as part of macromolecules in a previous lesson. We have reactants, which are the molecules that we put into a chemical reaction, and products are what we get out. We're going to break the bonds between atoms, whether they're covalent or ionic. We're going to break those, and those atoms are going to rearrange and form new molecules that are the products. That's what's happening in a chemical reaction. When those chemical reactions happen, they can be put in one of two categories. Do they give off energy or do they absorb energy? Now, you're probably more familiar with exothermic and endothermic, which is talking about really similar ideas. The only difference is those are only referring to changes in temperature, heat caused by the chemical reaction. When we use exergonic and endergonic, we're actually referring to any change in energy. So it could be chemical energy, it could be light energy, right? So it's just a little bit more generic. We're not relying solely on heat as the energy that's changing. And so exergonic is when a chemical reaction happens and it releases energy as heat, as light, as both, as a new form of chemical energy. That's going to be exergonic. Endergonic is when we have to put energy in to cause the chemical reaction to happen, more energy than it would release when the molecules reform. So exergonic and endergonic are going to be some important terms. All right. Let's see. That's what this is showing us here. Now, in this food calorimetry component to this lesson, what we want to understand here is that when we use that heat to break apart the molecules of this walnut, sorry. We use that to break apart the walnut. What's happening is that as those molecules break, that energy is being released. It's endergonic. This is to show us that there's actual energy in our food. And depending on the ratio of the macromolecules making up that food, we have differing amounts of energy. So there's a lot of protein in a walnut, but there's also a lot of oil. If you ever notice, like peanut butter is incredibly oily, right? Nuts typically are high in lipids. So there's actually a lot of energy in lipids, and they're going to give off a lot of heat when they burn, versus something that's just straight sugar isn't going to have as much energy as something that has a lot of lipids in it, right? They're very good at storing energy, and that's why they give off so much when we burn them. Understand this food calorimetry though, right? Just to kind of reiterate, have the setup here. We had 10 milliliters of water in this little test tube here, and we measured the temperature of that before and after. And the idea is the energy to increase the temperature of that water comes from the burning peanut. And we also are going to lose mass, walnut, not peanut. As we as we burn the walnut, we lose some mass. Now, matter is not created or destroyed in a chemical reaction. So what's happening is we burn that walnut. We're not destroying the matter there. We're changing into a new form. You'll notice that it's going to be releasing a lot of gases, and some of it stains the test tube here. Those gases are going to be things like carbon dioxide, and they're going to be still, those molecules are there. They're just now in a gaseous state. And so we can measure how much matter was converted in the chemical reaction to kind of get an idea of how the energy density of the food item, how much energy was released compared to the mass that was lost. So you do that by taking the calories and dividing it by the grams that were lost. Now, calorie is defined as the amount of energy required to raise 1 milliliter of water 1 degree Celsius. Now, this is a little c calorie, not 1,000 calories, but one, like not a kilocalorie like you would see in your food. Those are listed as a big C. These are little c calories that we're talking about here. So if we have 10 milliliters of water and we were to raise it, say, 20 degrees Celsius, we didn't have 20 calories, right? We raised 10 milliliters of water 1 degree. That's going to require 10 calories to move that much. So if we raised 10 milliliters of water 20 degrees, we would multiply that 10 by 20 to say, oh, there was 200 calories released there. And then we can see how energy dense or energy rich the food item is by taking that and dividing by the mass. So that's what food calorimetry does for us. It lets us measure the differences between different macromolecules and the amount of energy that they release. Something to keep in mind with that, though, is this process is not terribly efficient. Our little simple calorimeter here is losing a lot of heat and light energy. It's not all making it in the water. So we're probably underestimating the raw amount of calories that were released in this process. Another thing to keep in mind with that is that when we talk about how many calories you get from the food that you eat, right? This is going to be burning a lot of cell wall, cellulose, that you can't get any energy out of because your enzymes are not built for that. Remember, enzymes are substrate specific. And so your enzymes can't break down cellulose. So if you were to eat this walnut, you would get lots of energy out of it, but you wouldn't get as much energy as is truly being released as we burn it. Because when we burn it, it's breaking apart the cellulose. You can't do that. You can't get energy out of that cellulose. You're not getting that full value out of it. So when we look at our dietary calories, like what's on a food label, they're talking about 1,000 units of it. I don't particularly know why they chose to do that. Maybe to make the numbers look smaller and make us feel better. I don't know. But the numbers we're seeing there are actually based on the amount of food calories that you would get out of it. So it's the things that you can actually digest. So just something to kind of be aware of as we talk about those things. All right. I believe we talked about the energy of activation when we talked about enzymes in our macromolecules lesson. And that's what they do, right? Enzymes lower that energy of activation. This hump right here is not quite as high. Energy coupling is when we take one chemical reaction and use the energy released from that chemical reaction to feed a second one. This is what your cells are doing all the time, right? They're going to take this chemical reaction that gets energy out of the food that you eat and use that to build up molecules, and then use those built up molecules to feed other chemical reactions that you need to have happen. And that's what ATP is for here. ATP, if we want to focus on this part right here, there are 3 phosphates all jammed together. Those phosphates are ultimately negatively charged. To have 3 negatively charged molecules or parts of a molecule here, those do not want to be near each other. It's like a spring that's been loaded. It's ready to burst at the slightest need. That's why ATP is such a good molecule to be like our energy currency, to have that energy readily available whenever we need it in our cell, because we use the energy from the food that you eat to load up this this 3-phosphate combination here. And then whenever we need that energy in our cells, it very quickly we can pop off one of these phosphates and use the energy from that phosphate being released, that spring being released, to feed another chemical reaction. Let's see. Okay, there was another image showing it. There we go. That's what I wanted to see. We have ATP, adenosine triphosphate. We use that energy that's holding that 3rd phosphate on, we pop that off, and energy gets released. And then we're back down to ADP, adenosine diphosphate. Well, the mechanisms that of your cell that get energy from the food that you eat are going to use the energy from that food to actually force this a phosphate back onto ADP, and that gets you back up to ATP. And so that's how we get this cellular energy that we're needing to. A fun, kind of an interesting story that helps us understand kind of how our bodies maintain homeostasis is what happens with ATP in your brain. When you're awake, your brain uses more ATP than you are capable of replenishing using your cellular processes. And so as you use up that ATP throughout the day as you're conscious, you're slowly running out of it in the tissues of your brain. It's becoming ADP. We actually can use the 2nd phosphate. We can break that off and get some energy off of it as well. It's not as efficient, so our cells typically don't want to do this. But if our ATP gets low, it can use ADP for energy. Well, if we use ADP by breaking this phosphate off, then we only have 1 phosphate or a monophosphate, and that becomes AMP. When AMP levels start to increase in your brain, it is detected by a gland in your brain that's then going to release a chemical signal called melatonin. You may have heard of melatonin, right? People take it when they have problems sleeping. You naturally produce melatonin from a gland near your brain. When that melatonin gets released into your brain, it is what makes you tired. So when your AMP levels start to grow, that's how your brain figures out, that's how your body figures out that your brain's getting low on energy, and it essentially triggers you to go to sleep. When you're unconscious, the cellular processes of getting energy from the food that you eat can operate at a surplus, and you can rebuild those stores of ATP. That's actually why we need to sleep at night. Okay, I think we covered everything we need to in this